All right, great, thanks. So yeah, I'm Anukool, and I'm going to talk about some research that started off about 3 years ago when I was interning at Sprint Labs. And since then, with collaborators Mark Crovella at Boston University and with Christophe Diot, who's now at Thomson Research, what we've basically done is we've designed methods, designed algorithms for basically looking at net flow data collected across your network, right, and finding interesting events that hopefully you as operators are passionate about. Okay, so if you're only going to listen to one slide, this is it, right? The goal that's sort of that's driving our research is to eventually build a system, a general system that can detect and classify network anomalies, right? Not specific sort of port scans or DOS attacks, but something that's very general that can do, you know, operational events, unusual end user behavior, or even sort of malicious activity. And so really the central message of my talk is to sort of advocate this notion of network-wide analysis. And really to look at, the idea here is to look at your network as a single entity as opposed to as an individual link or a router, and to really devise methods that can detect anomalies once you sort of look at the network in this manner. And ultimately, I'm here to beg for your feedback. I mean, this research was really inspired by problems that you as operators face. So it would be great if you can, you know, catch me in the hall or something and just tell me what you think about this work. All right, so as I said, the main message here is network-wide traffic analysis. Can you guys hear me, or am I you can hear me, right? Okay, good. And by that, what I mean is to really look at the network as a single entity, right? So for instance, here's a toy network. It's actually Abilene, but it's a cartoon over here. And you know, if you look at this network as a whole, what you see is that, oh, you know, hey, there's something anomalous happening in the top 3 links, right? There's this spike in traffic, right? Or you could look at, for instance, the network again as a whole and see, hey, there's something anomalous happening at that bottom link. It seemed like an outage or something of that sort. And so really, to sort of get around these problems, what you really need to do is to simultaneously analyze traffic across your network. So sort of to divorce yourself from the, hey, let me look at traffic on a single link and see what's happening, and to look at traffic on all links in your network. So there are many ways you can do this, right? You can sort of rely on SNMP data, byte counts or something like this, pulled from, you know, the key interfaces in your network. Or you can look at, for instance, the traffic matrix and get the point-to-point demands, and that's exactly what we do. So in this talk, what we're doing is we're leveraging traffic matrices collected over a 3-week period from the Internet 2 Abilene network and the Diot research network, binned at 10 minutes. So both these are relatively large networks. I mean, they're not you know, hundreds of nodes, but they're you know, the Diot network is about 22 cities. The Abilene is about 12 cities across the US. All right, so why is this cool? Well, the real power of network-wide analysis is sort of shown here in an example. What I'm showing you here is basically a massive distributed DOS attack, right? That's arising from Atlanta, Houston, LA, and Indianapolis, and sort of you know, targeting some poor victim in New York. And what I've shown you here are the traffic flows for those 4 malicious flows, right? So the key point here is that if you were to look at one of these flows in isolation of everything else in the network, you wouldn't catch the anomaly. By the way, the anomaly is shaded in the gray bar over there. So it's really by fusing all these 4 traffic flows that the anomaly stands out, right? Because once you start looking at these flows across the network, what you see is that, hey, there's a little blip in each of these, right? And this blip is actually pretty small. It's 19 megabits or something like this. And only then you can say, hey, this is an attack happening. And what you've done actually in the process is you've identified the ingress points where this attack is entering your network. All right, so this is really hopefully I've convinced you that this is actually something that would be pretty cool if we could do this. But hey, this is actually quite hard because you know, I'm showing you here 12 point-to-point traffic flows from Abilene, and really what we have is 121 of these things, and these are horrendous structures, right? I mean, where is the signal? Where is the noise? Where are the anomalies? How do you mine this for the interesting events? Right? You could look at this sort of even manually, and you'd be, you know, it's too much data to handle. It's too much data to tame. It's too much data to extract meaningful information. Meaningful information from. And so that's really the question: How do you tame this beast, right? How do you analyze this and really start extracting the interesting events? And so this is what we have done. this is something that we did about 2 years ago, and what we have done is we have devised some methods, what we call the subspace method, to really address this problem. So at a very high level, the subspace method is basically an approach to separate normal and anomalous traffic, right? But it's drastically different from traditional intrusion prevention systems, which sort of look at traffic over time and say, okay, this is my model of traffic over time. This is what I've seen in the past, and this is what I see in the future, and this is an anomaly. Well, the subspace method takes a completely radically different approach. What it basically says is, you know what? I'm going to look at all the traffic flows in my network, and I'm going to find the patterns that are most common, that are most dominant across all these traffic flows, right? In a sense, like a democracy notion, right? What does everybody think is normal, right? And that's what normal is. And so once I've sort of tamed normality, right, I look at the remaining temporal trends that are exhibited throughout the network, and this is what anomalous is. And then what we do is we apply statistical thresholds to systematically sort of find the outliers in this anomalous subspace. So, I mean, I understand that I might have done some hand waving here, and this is a paper in and of itself that I've summarized in one slide. And again, I'd be very happy to show you the source code, to show you the algorithms, the math, and so forth. But let me show you some cool results that we found. So this is an OD flow from Washington to New York, from Abilene. And on the top plot, you're seeing byte counts. Middle plot is packet counts. Bottom plot is number of IP flows in that OD flow. In blue is the original traffic, which is noisy and complex. In green is what the subspace method thinks is normal. All right? That little red circle is an anomaly that the subspace method flagged as being anomalous. So we looked in a little bit, and we found that, hey, there's this one pair of IP addresses that sort of dominates all this traffic. And we dug around a little bit more, and we found that this was actually a bandwidth measurement experiment that the Stanford Linear Accelerator group runs, right? So, okay, this is not something that you'd start calling your manager about, but it's still interesting if you can detect something that is anomalous in this sense, because it could be overloading your router or causing unnecessary disruptions. But here's actually my favorite anomaly. This is again an OD flow from Sunnyvale to Chicago. Again, you're seeing bytes, packets, flows. Green is normal. What the subspace method thinks is normal. Blue is original traffic. And what we see is an anomaly in all the three views of traffic, right? So we dug deeper because we couldn't figure out what exactly was anomalous about this. But then we found that we had actually detected another anomaly in the Los Angeles to Chicago OD flow. So you're seeing an anomaly. You're seeing a surge in traffic from Sunnyvale to Chicago, and you're seeing a drop in traffic from Los Angeles to Chicago. We dug around a little bit more, and what this really was a multi-home customer, the California Research Education Network, that was routing its traffic around an outage in Los Angeles. So presumably this is something that operators would care about, because you could start ringing alarm bells if you saw just a Sunnyvale to Chicago and say, hey, this is a DOS attack happening. But by sort of looking at multiple traffic flows, you can say, hey, this is an operational issue and not a security issue, right? You can sort of start distinguishing between these things. All right, so here's a broad quantitative breakdown of the kind of anomalies that we found. We looked at 4 weeks of data. We found 483 anomalies. Most of these were, because the Abilene network is a very researchy network, most of these were sort of bandwidth measurement experiments, what we call alpha flows. We found some DOS attacks, some scans, some overloads, some weird content distribution going on, a few worms, outage events, traffic shifts, some things that we just couldn't classify, and then a small fraction of false alarms. But really, what I want to draw your attention to here is basically the remarkable spectrum of anomalies that you can detect over here. You're not sort of detecting one little thing, a DOS attack or a scan. You're detecting, in a very general manner, a whole range of events. All right, well, this is great if you can, it's great to say there's something anomalous happening at time t, but really what you want to be able to say is that there's something anomalous happening at time t, and it is a DOS attack, or it is a scan. And that's really what we've tried to do. We've tried to build methods to automatically classify these anomalies once we've detected them. And so again, our goal is to really classify anomalies without starting with a predefined set of anomalies or predefined set of rules, because that sort of confines you to whatever you've put in your snort signatures or whatever. You really want to be able to detect new kinds of events that happen, new kinds of worms, new kinds of applications. You want to find these things. So you want to adopt an unsupervised learning approach. This is what the mathematicians call it. And really the approach that we have taken is we have tried to leverage the information that's existing in NetFlow today. basically what we're looking at is we're looking at the header fields, right? The source IP, the source port, the destination IP, and the destination port. And in particular, what we're doing is we're measuring the dispersion in these features. What do I mean by that? Well, let's imagine that you have a massive distributed DOS attack happening, right? What are you going to see? You're going to see a dispersion in the source addresses. You're going to see a lot of source addresses, right? And you're going to see a concentration of traffic onto one victim. So by measuring the dispersion, perhaps you can start classifying these anomalies because this dispersion reveals the structure of the anomaly. All right, so the approach is really to leverage this dispersion in these header fields, right? And then to apply sort of off-the-shelf clustering algorithms. And here's an example. What we have done is we've taken 3 different kinds of anomalies. We've taken the code red worm scan. We've taken a single source DOS attack, one script kiddie attacking another script kiddie or attacking another poor grandma. And we've taken a third kind of more sophisticated attack, a multi-source, distributed attack. And what I'm showing you here is I'm basically showing you how these attacks are distinguished when you look at them by looking at, when you sort of look at them in this 2-dimensional view of source IP dispersion versus destination IP dispersion. Okay, so let me be a little bit more clear. So let's take, for instance, the red circles, right? These are the code red worm scans. What we see is that this falls in the region of concentrated source IPs and dispersed destination IPs, right? This is indicative of a massive scan because one poor infected guy is trying to infect others. So you have this concentration in source IP spreading out and propagating out to a whole set of destination IPs, right? Now let's take for example the multi-source DOS attack, right? This falls in the region of dispersed source IPs, right? A lot of guys sending traffic to one victim. And again, single source DOS attack is in the region of concentrated source IPs and concentrated destination IP because it's one guy attacking another guy. So what this plot shows here that these 3 anomalies, which if you were to just look at them on the surface, you can't really distinguish them. But when you look at them in this clustering framework, they effectively separate out. So this is encouraging because this means that you can apply an automated way of classifying these events. All right. Well, let me just summarize. What I've basically done is I've actually given you 3 papers for the price of 1, right? And there's a lot more here. And let me just summarize our results. Hopefully, what I've shown you is that network-wide analysis is actually a pretty powerful framework. You can detect a whole range of anomalies with low false alarms. And in our papers, we have actually done some pretty comprehensive synthetic injection of anomalies, and what we found is that these methods are pretty sensitive. Even if the anomaly is 1% of your background traffic, you can detect it with considerable effectiveness. And with regards to anomaly classification, I've just given you a flavor of the kind of work that we can do by looking at these clusters. You can separate these events, and you can also, in our papers, we've used these clusters to learn about new kinds of anomalies, new kinds of scanning behavior. So hopefully I've convinced you, or at least shown you methods and given you a flavor of the kind of methods that we're using to do general anomaly diagnosis. And really, again, as I said, you can look at my website. Here are all the papers. Our ongoing work is actually to take these algorithms from MATLAB scripts to actually building a system that would be of use to you. And this is really where I could I would really appreciate any feedback that I can get because if it's suggestions or data or deployment or any of this sort. Thanks.
Products, VJ Galileo, this is one of the products I would definitely buy. So if you can productize it and come sell it to us, I think we'll put our money where our mouth is. The other thing is we already have something similar to this in-house where we take our sensitive prefixes or sensitive /32s. We already get NetFlow data from all over the backbone, and we run our own in-house tools to see if traffic pattern to those particular prefixes changes. And if they we do some analysis, and if they change, we signal an alarm. This is much more general and much more applicable to the backbone in general, and this is something we would definitely like to see productized. So if you have any VCs, we can talk to them.
Maybe you could help us with some data. That would be nice.
Sure. Talk to me afterward. The question I had was, how were the traffic matrices gathered? What was were they pop to pop, edge to edge, or were they like node to node?
So Let me answer that. Again, we collected NetFlow data at each interface of the Abilene routers, the incoming interfaces, and then we fused them with routing data, and then we aggregated. We had router-to-router traffic matrices,
Okay.
but our analysis over here is at pop-to-pop.
Okay,
So-
so that's good enough. And the other question was the temporal patterns on your software, because I mean we also do the temporal patterns in our links, and they tend to, as you can see, vary day to day, hour to hour, and week to week.
Right.
So your software normalizes them according to.
Absolutely. Yeah.
Okay.
In fact, that is the key insight, because once you know that's actually the power of the method, because that's what you're actually leveraging. Right?
Yes,
The
that
fact
is the
traffic
problem we are struggling with, and that's what I wanted to get some more detail on. But I guess we can talk offline. on that.
Sure. Thanks.